What specific problem does your method of coherent chain of thought, COT prompting, aim to solve in the context of large language models? And how does it improve upon previous methods such as stepwise ICL?
The coherent chain of thought, COT prompting method addresses the limitation of stepwise ICL, where each reasoning step is treated in isolation, leading to suboptimal predictions. By integrating all previous reasoning steps into the prediction process, coherent COT allows the model to self-correct by considering potential errors from earlier steps, thereby enhancing overall prediction performance. The method demonstrates that treating COT as a holistic process, where intermediate responses are plugged back into the input prompt, results in better inference outcomes compared to the segmented approach of stepwise ICL. Additionally, coherent COT's sensitivity analysis reveals that it is more affected by errors in intermediate reasoning steps than inaccuracies in final outcomes, emphasizing the need for improved accuracy in these steps. Overall, coherent COT not only improves prediction accuracy, but also provides a framework for better handling reasoning errors through error-aware demonstrations.
How does the proposed coherent COT method work? Please illustrate the process step by step, particularly highlighting the differences in the training and inference stages compared to stepwise ICL.
The proposed coherent COT method operates through a two-step reasoning process that integrates previous reasoning steps into the final prediction, contrasting with the stepwise ICL approach. In the training stage, coherent COT utilizes a single transformer model to predict the intermediate response, #z_q, and then incorporates this prediction back into the input prompt for the final prediction, #y_q. This holistic approach allows the model to leverage both the original inputs, x_i, and the intermediate responses, z_i, enhancing the model's ability to self-correct by considering potential errors from earlier steps. In contrast, stepwise ICL treats each reasoning step in isolation, where the intermediate response is predicted separately and does not utilize the previous reasoning context in the final prediction. During inference, coherent COT is more sensitive to perturbations in the intermediate reasoning steps, emphasizing the importance of accuracy in these steps for overall performance, while stepwise ICL only focuses on the immediate task without integrating earlier reasoning.
Can you provide a simple yet illustrative example that demonstrates how the coherent COT method operates, particularly focusing on how it integrates earlier reasoning steps into later predictions?
An illustrative example of the coherent COT method can be seen in a reasoning task where the model is asked to solve a mathematical problem. In the first step, the model predicts an intermediate response, say, #z_q, based on the initial inputs, x_i, and the reasoning steps provided in the prompt. Instead of treating this prediction in isolation, coherent COT integrates #z_q back into the input for the next step, forming a new prompt that includes both the original inputs, x_i, and the intermediate response, #z_q. This holistic approach allows the model to adjust its final prediction, y_q, by considering the context of the earlier reasoning steps, thereby enhancing its ability to self-correct and improve accuracy. For instance, if the model realizes that #z_q was influenced by an error in the previous reasoning, it can modify its final output accordingly, demonstrating the effectiveness of integrating earlier steps into later predictions.
What are the specific theoretical or practical benefits that using coherent COT offers over stepwise ICL? Please discuss the enhancements in prediction performance and any improvements in efficiency or generalization capabilities.
Using coherent chain of thought, COT, offers significant theoretical and practical benefits over stepwise in context learning, ICL. Theoretically, coherent COT enhances prediction performance by treating the reasoning process as a holistic entity, allowing the model to integrate information from all previous reasoning steps, which facilitates self-correction and improves accuracy. Practically, this approach leads to better generalization capabilities, as evidenced by the model's superior performance in inference tasks when trained with coherent COT compared to stepwise ICL, which only focuses on immediate tasks without considering earlier steps. Additionally, coherent COT's sensitivity analysis reveals that it is more responsive to errors in intermediate reasoning steps, suggesting that addressing these errors can further enhance overall performance. Overall, coherent COT not only improves prediction accuracy, but also fosters a more efficient learning process by leveraging the interconnectedness of reasoning steps.
How did you validate or test the performance of the coherent COT method? Please elaborate on the experimental design, the datasets used, and the metrics you employed to measure its effectiveness compared to traditional methods.
To validate the performance of the coherent COT method, we conducted experiments using 4 large language models, LLMs, GPT-3, 5 Turbo, GPT-4o Mini, Gemini Pro, and DeepSeek 67b. We utilized 5 datasets from 2 benchmarks. The BBH benchmark, which included reasoning tasks such as disambiguation QA and tracking shuffled objects, and the GSM-8K benchmark, focusing on arithmetic and grade school math problems. The experimental design involved comparing the performance of the models using standard COT prompting without incorrect reasoning paths, with OIR, against our proposed method that incorporated incorrect reasoning paths, with IR. We measured effectiveness through performance metrics, specifically accuracy, and observed significant improvements in several cases, such as a 60% increase for Gemini Pro in the tracking shuffled objects dataset and a 17% increase for DeepSeek 67b in the penguins in a table dataset. These results highlight the positive impact of the coherent COT method on enhancing reasoning capabilities compared to traditional methods.
What limitations or potential drawbacks did you identify with the coherent COT approach? Discuss any constraints regarding its applicability, complexity, or sensitivity to errors at different reasoning steps.
The coherent COT approach, while demonstrating superior prediction performance compared to stepwise ICL, introduces several limitations and potential drawbacks. Firstly, it requires training the model on the entire reasoning chain, which alters the model's optimal parameters and complicates its behavior, leading to uncertainty about which steps in the reasoning chain are most sensitive to errors. This sensitivity analysis revealed that the coherent COT model is more susceptible to noise in intermediate reasoning steps than inaccuracies in final outcomes, indicating a heightened risk of error propagation during inference. Additionally, the complexity of incorporating both correct and incorrect reasoning paths in demonstrations may increase the cognitive load on the model, potentially leading to confusion if not managed properly. Lastly, the necessity for sensitivity analysis and error-aware demonstrations adds layers of complexity to the implementation of coherent COT, which may limit its applicability in real-world scenarios where quick and efficient reasoning is essential.